Plasma and fusion demonstrations. Part of a series of activities in plasma fusion physics to accompany the contemporary physics education project chart, Fusion, Physics of a Fundamental Energy Source. Magnetic confinement demonstration, motion of charged particles in a magnetic field. In this segment we will view the effects of a magnetic field on moving charges. The basic equipment. The equipment used for the following demonstrations includes an oscilloscope and a power supply. A solenoid, connecting wires, and iron bar magnets will also be used. Solenoid magnetic field source. In addition to a bar magnet, a solenoid will be used in later portions of this demonstration to produce a variable magnetic field which is also more uniform than that of a bar magnet. In order to intensify the magnetic field that will be produced, some iron bars are placed inside the solenoid. The ends of the solenoid are then firmly taped with duct tape to keep the bars from falling or magnetically surging out. Setting up. We will first use a dot display on the oscilloscope. Positive and negative leads are connected from the power supply to the bar-filled solenoid. This will allow use of the solenoid as a source of a variable magnetic field in addition to the fixed magnetic field of the bar magnet. Reviewing the right-hand rule. The right-hand rule describes the relationship between the conventional current, magnetic field, and the force acting on the conventional current in that magnetic field. Please keep in mind that for a beam of electrons, the conventional current is in the opposite direction to the velocity of the electrons. The conventional current direction is in the direction of the equivalent positive charge. In this model, the red arrow represents the conventional current. The white arrow represents the magnetic field. The blue arrow represents the resulting force acting on the conventional current in the magnetic field. These are related by various representations of the right-hand rule. This is one example. With the fingers pointing in the direction of the conventional current, curling the fingers toward the direction of the magnetic field, the thumb points in the direction of the resulting force. Turning the display, it is seen that the force is always perpendicular to the plane formed by the field and the current, although the field and the current can have any angle between them. The effects of a bar magnet on a dot. Slowly bringing the bar magnet toward the screen vertically from the top, perpendicular to the electron beam which is traveling from the back of the oscilloscope to the front, produces a horizontal deflection of the beam. With the north pole of the magnet oriented on the bottom, the deflection of the beam is toward the left, as indicated by the well-known right-hand rule. Conversely, with the south pole of the magnet oriented on the bottom, the deflection of the beam is toward the right. Slowly bringing the bar magnet toward the screen horizontally from the side, again perpendicular to the electron beam which is traveling from the back of the oscilloscope to the front, produces a vertical deflection of the beam. With the north pole of the magnet oriented on the left, the deflection of the beam is upward, also as indicated by the well-known right-hand rule. Conversely, with the south pole of the magnet oriented on the left, the deflection of the beam is downward. Bringing the bar magnet toward the screen horizontal to the electron beam produces little if any beam deflection. Magnetic fields parallel to velocities of charged particles exert zero force on moving particles. Moving the beam to the side, however, results in a diagonal velocity of the particles with components from oscilloscope back to front and also side to side. These side-to-side components are perpendicular to the horizontal magnet and to the horizontal magnetic field it produces just inside the screen of the oscilloscope, and therefore a slight deflection is observed. The effects of a variable magnetic field on a dot. Increasing and decreasing the current through the solenoid will result in increasing and decreasing magnetic field strength. Again, aligning the magnetic field from the solenoid parallel to the beam produces little if any deflection. When the dot is moved to the left side, the side-to-side component of the electron beam is perpendicular to the magnetic field. Therefore, a deflection is observed and increases as the magnetic field is increased in intensity. Although the parallel component of the velocity is unchanged by the magnetic field, the perpendicular component is forced to continually change direction. This results in a helical motion of the electrons. Notice that the dot on the screen gets closer to the center of the screen during the deflection. This shows that the electron beam producing the dot is being confined rather than continuing to diverge outward. This is the same effect as that produced in magnetic confinement fusion reactors. When the beam is moved to the right side, the deflection is in the opposite direction. These results are observed again from a closer vantage point. The effects of a bar magnet on a line. The presence of a magnetic field parallel with the center beam has no effect on the electron beam hitting the center of the screen. However, beams hitting to the left or the right have velocity components perpendicular to the magnetic field. These beams are then forced onto helical paths. The effects of a variable magnetic field on a line. Again, increasing and decreasing the current through the solenoid will result in increasing and decreasing magnetic field strength. As observed with the bar magnet, the presence of a magnetic field parallel with the center beam has no effect on the electron beam hitting the center of the screen. However, beams hitting to the left or the right have velocity components perpendicular to the magnetic field. These beams are then forced onto helical paths. This deflection is observed to increase as the magnetic field is increased in intensity. When the magnetic field is reversed, so is the direction of the deflection. These results are observed from a closer vantage point.